Hey chemistry students, this is Mrs. Miller, and today we're going to be talking about atomic nuclei and nuclear stability. So this will be our last section of notes for this unit. You guys will likely be doing this in class, but if you're listening to this outside of class, we need to talk a little bit about charges. So if you're in class, you're going to be doing a magnetic demo, but what we know about magnets is like charges do what? Like charges, of course, are going to repel one another. So if I have a positive charge here and a positive charge here, they really don't want to be together. So you can keep pushing them really, really close. If you've ever done that with a magnet and you put the two like north ends together, they don't want to be close to one another. It takes a lot of effort for you to push them there. However, we know that a positive charge and a negative charge, so opposite charges, attract. So those guys are going to want to be near one another. All right, our next question here is what makes up the nucleus? Well, of course, the thing that makes up the nucleus, we have our neutrons and protons that are inside of the nucleus. And what charges do these have? Well, we know that neutrons are neutral, meaning that they don't have a charge. However, protons are positive. So we have something that has no charge associated with them, and then we have a positive charge associated with them. So how are we able to keep that nucleus together when we only have these positive charges? Well, it's the neutrons that are going to help with that, because our neutrons are going to act as spacers to make sure that those two positive charges don't come too close to one another. So as I had just mentioned, how does the nucleus stay together with all these positive charges? And remember, it's positive because of our protons. Well, that is something called the strong force. The strong force is the interaction between protons and neutrons that bind nucleons together, or all pieces of the nucleus. So a nucleon is all pieces of nucleus. So what that means is we're going to have this strong force is going to be much stronger than electrostatic repulsion forces over short distances. So we know that neutrons are going to act as spacers. Because if we give them enough space, and we have our positive proton and then our neutron and another positive proton, there's hopefully enough space between them that we're not going to see that nasty repulsive force that we did before. So in a very large nucleus, some protons and neutrons get too far apart, and now the nucleus becomes unstable. So I always think about this like hang on to tennis balls. If I give you a few tennis balls, great, you're able to hang on to those for quite some time, or even ping pong balls. And as I keep handing you more and more, at some point, maybe you're using your full arm, or some kids might even use their shirt to hang on to them, but I'm going to eventually overload you. And that's where we don't have enough force to keep that nucleus together anymore. And that's when we end up with things that become unstable, and that's where we have radioactivity. Another good question to answer is, where does the strong force come from? Well, the first thing is what we see with binding energy. So binding energy is the energy released when the nucleus is formed from separate protons and neutrons. So by themselves, protons and neutrons are going to have some energy, and when they come together and they actually form that nucleus, we're going to see some of that energy leave. So protons coming together with neutrons, that creates our nucleus and extra energy. So that energy goes away, goes outside of the nucleus. So the nucleus has lower energy than them by themselves. Lower energy means it's more stable. So where does this binding energy come from? It's from something called the mass defect. The mass defect is the mass of the nucleus is less than the mass of the neutrons and protons added together. So what we're going to see with that is that the overall nucleus weighs less than the neutrons and the protons, and that's because of that loss of energy that's going out of there. It's enough that it actually lowers the mass with Einstein's equals mc squared. So here's just a short little example of that. We have our helium atom. Sometimes, remember, we referred to this as our alpha particle. If you guys remember back to that. Okay, so we have our alpha particle here. It's made up of 2 protons and 2 neutrons. So naturally, we think that the mass of this is going to be 4 AMU, or atomic mass units. What we actually see is that the mass of a helium atom is 3.97 AMU. So it doesn't look like a whole big difference, but that little difference is enough to change that amount of mass in that nucleus, or that mass defect. So we can use E equals mc squared to calculate the amount of energy released. We're not actually going to have you guys do that in class. Just know that we can take energy, turn it into mass, and vice versa with Einstein's theory there. We are talking about large amounts of energy, much larger than what we're going to see with chemical reactions. Nuclear reactions tend to have way more energy with them, whether it's fission, fusion, or any of this information. The nucleus harnesses a ton of energy, whereas chemical reactions, while they might be loud, they might be explosive and things like that, the nuclear energy is much, much higher, which is why we don't use that very much at all. Scientists are going to study that. As chemists in high school, we do not, because it's way too dangerous for us. The next thing that we want to talk about is actually predicting the nuclear stability. So how stable is the nucleus that we're looking at? Because we have many nuclei that are going to be very, very stable, and then we have a ton of them who are also going to be very unstable. So not all nuclei are stable. Kind of as a rule of thumb, the further that you go down on the periodic table, the less stable they become, because they're holding too many ping pong balls in their arms, right? In their nucleus, it's just getting too big. So we have 2 methods of predicting stability. And our first one is going to be binding energy per nucleon, or nucleus. So the higher the binding energy per nucleon, the more stable the atom. So when we have more energy going in there to create our nucleus, it tends to become more and more stable. Iron and nickel are actually the most stable atoms on the chart, and these are why we are going to see them forming Earth's core. Oftentimes with stars, as they get really old, they tend to get that iron and that nickel in their cores as well, and now they're becoming stable, and they actually eventually run out of fuel, and then they don't work anymore. So that's the most stable that we can see with the atoms. So here we see a little chart of that. We can see way down here is the mass number of the nucleus. We start off with helium. So obviously that one is hydrogen. That one is going to be the smallest. And as we go up on here, you can see we get to some more stability up here. So as we go higher, it's a little bit more stable. And you can see then we see that it starts to drop. And uranium, which is uranium-238 in this case, so 92 protons in that uranium and quite a few neutrons, obviously. Because that is such a large nuclei, we're going to see it's going to become less stable. The other method that we can use to predict nuclear stability is the neutron to proton ratio. So how many neutrons are there, how many protons are there, and are they about equal? So I'll show you guys a graph on the next page, and it's going to include this band of stability. So what we tend to see is that small atoms tend to be very stable. Their neutron to proton ratio tends to be 1, and that indicates that for every 1 neutron we have a proton, so we have spacers in there to keep those protons at the perfect distance. However, we get to these large atoms where the neutron to proton ratio is now 1.5. So that means we have more neutrons than we do protons, and we almost have too many spacers in there, and our nucleus is going to become unstable because it can't hold all those pieces in the nucleus anymore. So I'll talk about this shaded band of stability on the next slide. So here we have that band of stability in that graph that I was talking about. So we can see that this shaded yellow area is where we are going to see stable, more stable elements. So what we notice is that obviously as you get a little bit larger, your NZ number tends to become higher in that 1.5 range. As you go above this line, you're no longer stable. Here's our band of stability, obviously is very low down here, and our NZ number is 1. One interesting thing to note is that we stop actually plotting after element 83. The reason why that is because they are no longer stable past that point, and we have quite a few elements past that, but their NZ numbers are above what we want in this band of stability, so they don't fall into that anymore, and they are very, very unstable, therefore they are radioactive. Uranium is a good one, polonium. Those are all great examples of what we see with the radioactives because they're so large that they aren't stable in the nucleus, so they start to decay quickly. So in review here, we have without the strong force, the protons in the nucleus of an atom would repel each other and the nucleus would blow apart. So we need those neutrons in there to provide the spacing of those protons so they don't repulse one another. Energy released in any nuclear reaction, nuclear formation, fission, or decay, comes from the binding energy, or that energy where the protons and neutrons come together to form the nucleus, which results from a little of the mass of the nucleus being changed into energy. And again, that goes back to E equals mc squared. So if you guys have any questions, let us know. Otherwise, have a great day.